All right, last section of chapter 6, 6.8, standard enthalpies of formation. So we were just talking about heats of reaction and Hess's law. Well, this is kind of a subtlety or a nuance and a continuation of that. Standard state of a substance is the state in which the substance is most stable at 25 degrees Celsius in 1 atmosphere. The standard enthalpy of formation, delta H naught F, is the enthalpy of formation of 1 mole of a compound from its constituent elements in their standard states at 25 degrees Celsius and 1 atmosphere. H2 plus O2 yields 2H2O. Note that the delta H naught F of any element in its standard state is 0. It's a very important part. The delta H naught F of any element in its standard state is 0. Okay, so from there. Some standard enthalpies of formation at 298 K, which is our 25 degrees Celsius. Methane, negative 74.6. Water, this is one that's very important to recognize, is liquid and gaseous water have a different enthalpy change, or different enthalpy of formation change. So essentially, there's a different amount of energy to form liquid water than there is gaseous water. Okay. Now, how does that table is really more or less like, oh, neat, great, happy to hear that. This right here shows us when using delta H naught F to calculate our delta H reaction, our delta H reaction is equal to the sum of our heat of formation of our products minus the heat of formation of our reactants. So this is something that people simply kind of characterize as products minus reactants. That's all. But what it is the sum of the enthalpy changes, or the enthalpy or formation of those reactants minus the sum of the enthalpy of formation of those reactants. When the reaction involves multiple moles of products and reactants, well, then you have to multiply that number of moles by those reactants and multiply that number of moles by the products. So that's something to take into consideration. Calculate the delta H naught reaction for the complete combustion of 1 mole of propane, C3H8, at 25 degrees Celsius and 1 atmosphere. Okay, so here's our reaction. We've got C3H8, O2, CO2, and H2O. Now, you are not expected to have these committed to memory or anything like that. These particular values. Generally, they're going to be provided in the problem. Now, I will go ahead and write them down next to each one of the substances. So C3H8 has a value of negative 103.8. O2, this is one of those things that, well, it's in its kind of elemental state, and that happens to be, and as a result of that, at room temperature, it's 0. CO2, negative 393.5, and H2O is negative 285.8. Okay, so all that we have to do is do products minus reactants. There's a little bit more to it though, because we have these coefficients. So all of these values are for 1 mole of this substance. So what I'm going to do is I'm going to say 4 times negative 285.8, because I like to start with the products and sum all those up. 3 times negative 393.5 minus, and then negative 103.8 plus 0. Okay. So my products end up being 4 times negative 285.8 equals negative 1143.2 plus 3 times negative 393.5 equals negative 11 80.5 minus negative 103.8. So negative 1180.5 plus negative 1143.2, negative 2323.7. I'm going to put that still in parentheses, minus negative 103.8. And so that would effectively be negative 2323.7 plus 103.8. And I'm left with negative 2219.9 kilojoules for this overall reaction. So delta H RXN naught is equal to negative 2219.9 kilojoules. All right. So that's kind of all there is to that sort of problem. And so there can be problems that are a little bit more involved. So this sort of thing can be employed for Hess's law calculations, in which case, what are you doing? Well, you're figuring out the heat of reaction of all of the different reactions and then manipulating them and using Hess's law to figure out an overall reaction. But that would be kind of the addition of two concepts. I hope this is helpful. Chapter 6 is a beast, but you're doing great. Keep it up, and I'll see you in Chapter 7. Stop.